Okay, so welcome back. What we're going to talk about now is some of the more hardware-specific things that you need to consider on modern computer architectures, particularly two sort of classes of hardware: vectorization hardware, which I'll talk about in this first lecture, and then memory hardware, which I'll talk about in the next immediate lecture. And we'll do two lectures back to back, and then the rest of the afternoon you can have to do go through the practical sheet where there's practical examples on vectorization and on memory optimization. Although part of exercise 4, which is optimizing the molecular dynamics code, also depends quite heavily on memory optimization. So as usual, if you have any questions, please feel free to put them in the chat, to interrupt and ask a question directly, to raise your hand, any of these kind of things. But in lieu of questions, I shall get going with a lecture. And really what we're looking at here is, we've been through some of the common things that you can look at for optimizing with the compiler, and in general what computer hardware and what hardware inside a computer node looks like. But now what we're looking at is some of the more specific details which modern CPUs require you to use to get good performance. And vectorization is one of these things that has been included routinely in processors for sort of the past 10 or 15 years, but is over time getting more and more important for overall performance. Actually less so on these AMD processors, because AMD have made the decision to go not hugely wide with their vectorization. So the vectorization capabilities you have inside these AMD EPYC Rome processors is similar to what you had on Archer on the previous system here, which was 7 or 8 year old Intel Ivy Bridge processors. But they do have vectorization, and to get the best performance on a processor, you need to use it. And also all the other processors we see around, which are used for scientific computing, Intel processors, A64FX from Fujitsu, these kind of things are very heavily vectorized. So it's common in the latest Intel processors to have sort of 4 times more vectorization than these AMD ones, and likewise in the A64FX. So that means it's something that if you can optimize your code for vectorization, then it won't go to waste, because porting between systems is still likely to be important, and it looks like it's going to become more important going forward. Okay, so vectorization has been around for a while, actually since the late 90s, early 2000s, when it was started to come into processors mainly to add graphics functionality. If you can remember that far, Intel started making things called MMX processors, which would speed up audio processing and video processing by your main CPU. And partly that was to allow them to build systems without graphics cards in them, or with reduced graphics card functionality. Vectorization is also a much older technology than that. So we've had vector supercomputers for a long time. Some of the early supercomputers were very vectorized. Although it should be said that the kind of vectorization we have in processors these days is slightly different to a old school vector supercomputer, where you literally had sort of one controlling process, and then lots of workers all doing the same thing. Here we've got vectorization at the CPU level, which lets us, for each CPU core, do multiple bits of work at once, but it's a lot more fine-grained vectorization than we used to have before. Anyway, so vectorization is a form of SIMD processing, single instruction, multiple data. So this means your program can spit out an instruction to be calculated on the processor, and add and multiply some other kind of operation, a load, a store. And that operation will be executed by a vector unit, but that vector unit won't just work on one bit of data, it'll work on a group of data at once, a vector of data at once. Okay, we have multiple different sort of names for vector instruction sets. Intel are on sort of AVX, AVX2, AVX512. AMD follow that sort of AVX notation and are on sort of AVX2 here for the Rome processors. If you were going to look at an ARM processor, for instance, you'd see them talking about SVE or Neon instructions, which are their sort of equivalent vectorization. In fact, the ARM processors of the future have quite nice vector functionality in this SVE approach, but probably too much detail. You don't need to worry too much about that. And yeah, as it says here, typically what we do is the single instruction operates on a vector or a set of vectors of data, which contain more than one data entry. So could be two, could be typically 4 double precision floating point numbers for this AMD processors on Archer 2. If you go to something like Intel's sort of Skylakes and newer processors, you're looking at 8 per floating point unit, so 8 double precision numbers at once. Same with the A64FX. And actually, some of those architectures can have 2 floating point units per core, which means you can do up to 16 things at once, 16 of the same instruction on different bits of data at once. The nice thing about it, of course, is that if you can use the vector instructions, you get a performance boost. So instead of doing 1 floating point operation per cycle or per group of cycles, you're ending up doing 4 floating point operations per group of cycles, or 8 or 16. And that means you can get 4 or 8 or 16 the amount of data process or calculations done if you can efficiently use these vector units. And that's the challenge here. How do you efficiently use these vector units? There are a number of different ways to program vector hardware, but like everything else we've looked at here, what we advocate is using the compiler to do this for you. So we're not advocating, necessarily writing assembler code or intrinsics code, which includes specific instructions to target the vector units. What we're saying is, ideally, the compiler understands the hardware you're running on, and it can convert your code into something that can use these vector units. But we may, as we'll come to see, have to do some work to help the compiler identify what can be vectorized, modify your code potentially so it vectorizes well, and then the compiler can do it for you. It is possible, of course, to program these vector units directly, just like you can write assembler code or instructions or operations directly. Just the nastiness of that, of course, is that once you start programming directly for a vector instruction set, your code becomes non-portable. So if you'd have written your code for Archer, which was Intel Ivy Bridge processors, and vectorized it there, once you come to port it to Archer 2 or to another system, you have to rewrite the vector bits because those instructions won't work anymore. And so ideally, we can work through the compiler, use the compiler's functionality to automatically generate code which are executables which exploit the vector units and leave it at that. The compiler, though, the issue with the compiler is it has a fair number of restrictions on what it will do in your code to turn it into something that will vectorize or uses vector hardware. The key one of those is that in general, the compiler will only vectorize loops and specific kinds of loops. And in general, the compiler will only vectorize your innermost loop. So if you have nested loops, a loop inside a loop inside a loop, your compiler may only vectorize, it will generally, by default, only vectorize that innermost loop. And so we can go on to see that can have performance impacts, but there are ways to get around these mitigations. Now, of course, it's worth saying that if your code doesn't vectorize, it doesn't mean it won't run on the processor. It just means you're not getting the full performance out of the processor. And you can see from this idea that we only vectorize loops, that if your code is written in such a way that, or your algorithm is structured in such a way that it doesn't work on loops, it works on linked lists or other data formats, then of course you're not going to get the best use out of these vector units. And that's just something you either have to restructure your whole application to deal with that, or just accept that your kind of code can't easily exploit the vector performance. In very much the same ways, some codes can be ported to GPUs easily and run there and get good performance, and other codes can't because of their structure, or it would take a lot of effort. And in a lot of ways, we can think of vector units on CPU cores in having very similar functionality to GPUs. The GPU, in an abstract way, you can think of as a very big vector unit with lots of vector width in it, so that it can do many instructions at once. But fundamentally, it's a reduced complexity vector processor, and it has some other things. I mean, a GPU has generally has some faster memory and things, cache and things like that, but in a lot of ways it uses a lot of the same characteristics as CPU vector units, just on a bigger scale. So the challenges that you may have porting a code to a GPU are very similar to porting efficient code onto vector units. Function calls are an issue, branches are an issue, data access patterns are an issue, things that are not well-defined loops are an issue. So we'll come on to discuss all of these things. Yes, so if we consider the AVX or the AVX2 vector configuration, something like this down the bottom here, it has generally a register width of 256 bits. That means it can store 256 bits in the vector register, each entry in the vector register. And in general, a lot of our scientific applications work with double precision numbers, which generally are 64 bits. So that means you can store 4 double precision numbers in a vector register. And if you can get if your code is amenable, then your application can do 4 operations every clock cycle. So an example here would be this loop. We have this for loop or this do loop, where we take B, add it to C, and store it into A. If we didn't vectorize this, we have to go through each element in turn, 0, 1, 2, 3, or 1, 2, 3, 4, and issue an instruction each time we go around the loop. But if we vectorize this with an AVX instruction where we've got 4 things we can do at once, then actually it's akin to expanding, unrolling this loop and doing A0, A1, A2, and A3 all in a single clock cycle. And of course, that applies to all the operations in this loop. This loop looks simple. It looks like you've only got one line here. Although I just noticed, of course, I have a nasty little mistake in that, which I should correct. Give me a second. My C is correct pseudocode, but not correct code. I was missing a termination character. Anyway, it looks like we've got a single line here, and so you look at that naively, you could think that this is going to turn into one vector instruction. But of course, this single line of code here, the same in Fortran, is broken down into multiple actual instructions. So there's a load instruction for B, a load instruction for C, an addition instruction for B plus C, and a store instruction for the result into A. So we've got 4 instructions, and all of those are going to have to be vectorized to get good performance. So we want to, the instruction set is not just doing vector things for adds and multiplies and subtracts, but it's also loads and stores and those kind of associated things. So the compiler ideally will come along and it will turn the load of B into a vector load of B and load up 4 elements of B into a register at once. And it will also turn the load of C into a vector load of C and load 4 elements of C up at once, offset by the loop counter, of course. So it will go 0, 3, 0, 4, 8, 12, 16. And then it will do the vector add of those two vector registers in a single instruction, and then it will do a vector store of the result into A. Okay, so for this vectorization to work, of course, it should hopefully be evident to you that we need our sort of data to also be aligned. So we need to be adding the same elements of B to the same elements of C to get to store into the same elements of A to get our vector ducks in a row and get our good performance here. And that's not to say you can't do some vectorization where you're accessing different data in different patterns, but we can come on to see that that may cost you some kind of performance. And the vector units can also work on different sizes of data. So you don't have to just do double precision numbers. It can also do single precision functionality as well. So you can also do 8 single precision numbers at once, or 4 double precision numbers, or potentially 2 extended precision numbers as well. And actually, if you've followed computing and modern hardware much recently, there's been a lot of debate and work on including new vector lengths for machine learning code particularly as well. So machine learning code quite often uses smaller data types than 32-bit, so 16-bit, 8-bit. And so a lot of the new processors that are come out with functionality which will do half precision. So bfloat 16 kind of functionality where you could do 16 half precision numbers at once as well. But that's not something we need to we can really exploit here on the AMD processors for Archer, but for future processors, that kind of functionality is coming in. So the AMD processor has a number of these vector units per core, and that should say 2 of these vector units per core. They're what's called symmetrical units, so they sort of do the same. They do the same functionality, but only one of them supports some of the legacy instructions. That means that if you bring a code along which has been ported to has got some intrinsics or some hard-coded vector instructions for some of the older instruction sets, SSE, MMX, x87, then you won't be able to use both the vector units. You'll only be able to use one of them. Again, this is part of a reason that we don't like suggesting you program directly in these intrinsics. And to slightly muddy the waters a bit here, actually the vector instructions have a longer latency than a single cycle. And this is quite common for CPU instructions, but getting into heavy details a little bit here. When you start a vector instruction off, it doesn't complete the next clock cycle and you get your result. Actually, on the AMD processors, it takes generally 6 cycles before you get your result. So that's generally not a problem because these vector units are pipelined, which means you can start off the instruction, and then the next clock cycle you can start off another instruction, and then the next clock cycle you can start off another instruction, and you can have 6 of them at once, all going at different stages in the pipeline. And once you've filled that pipeline up from the beginning, when you're first from your first vector instruction, 6 cycles in, you'll start to get results. And once the pipeline's full, if it stays full, you should get a vector result every clock cycle. And so that means that if you're vectorizing well and you've got lots of vector instructions, once you've filled up your vector pipeline, then you don't really have any additional overhead for this latency of 6 cycles. You just get your results out and you vectorize, you get good performance. The caveat, of course, is that this means that vectorizing small amounts of work is probably not very efficient, because if you say only end up with 4 vector instructions and you vectorize them, you will get some benefit, but because your pipeline took a bit of time to start up before you start getting results out, you don't get your full 4 times, 8 times speed up that you would like. So it really means that for vectorization to be efficient on this hardware, we want quite large loops doing similar stuff on similar data, so that we keep our vector pipelines full and processing data as we go through. Effectively, it means lots of small loops is probably hard to get good vector performance on these processes with, whereas a smaller number of large loops will give you more beneficial vector performance because of these startup overheads that you have. So, as I say, if you have any questions, do shout at me. I can appreciate that a lot of this is quite abstract until we've looked at it in more specific detail. So, if it's not making sense, do let me know. So the compilers that we have nowadays are generally quite good at generating vector instructions, as long as your code is easily sort of amenable to that vectorization. Didn't always used to be true. So if you went back 5-10 years, then some compilers were much better than others at generating vector instructions. But in general, they're all doing quite a good job these days. There's a good question here, Michael. Is there any point using vectorization when there's no temporal reuse of the same data from the cache if it's only read once? Yes, yeah, there still is some use in that, because at some level you will. It depends on how your code's working. If you really are truly memory bound, completely memory bound, i.e. you spend all your time loading data into cache, processing that data once and then storing it out, and you don't ever do anything intermediate inside there, then in general on these processes, your performance will be gated on the memory bandwidth, and vectorize or not vectorize will not help you. But if there is other work going on in there which you're not always loading data in from memory to cache and then just using that data once and going away, but you're doing other things at the same time, because the way the cache hierarchy works, you load contiguous data into cache, and then from the cache you can load vectors directly into a processor. You can still more efficiently process that data by loading it into the high-level caches and get it processed than if you were doing it one element at a time. But it sort of really depends on the application profile a little bit there. If it's truly streams-like, in that you're only ever processing data streams and you're only ever processing that data stream once and then you're getting rid of it, then you may not see much any benefit on these processes from vectorization. But most programs are a bit more nuanced from that, and actually you have some other work going on and some reuse of data in there. It also depends a little bit on the spatial layout of your data, because as we'll come on to see, vectorization is really only generally efficient if you're working on contiguous data, so data which is in contiguous chunks in memory. Otherwise, you spend a lot of time moving the data around to fill up your vector units. Now, again, processors and compilers are getting better at this, and certainly some of the newer processors from Intel and the newer vectorization instruction sets, and a lot of the latest ARM vector instruction sets with the SVE do a much better job of packing data together and allowing you to do that. But in general, contiguous data is what you want. Okay, so in general, and these are general rules. There are specifics which may muddy the water a little bit for some things, but in general, the compiler will only vectorize loops, as we've said, and by default, only the innermost loop in your loop nest if you've got multiple loops. And the compiler really wants to look for patterns where it can see that it can vectorize the data. So because it's doing this job of taking a chunk of data out of cache load it into a vector register, and then working on that entirety of that data in the vector register. It wants to be able to see your data access patterns, where, you know, how you go through your data, your arrays, whatever you're storing and processing, and check that that is going to work in a safe way, but it's not going to end up corrupting some data because actually you didn't expect all that data to be processed. At the outset, you're often asked, people often wonder if their code is vectorizing well or not before they've done any work on it, and it's a perfectly sensible thing to check along with your profiling and some of the profiling data you can get from the hardware counters, like we saw from Cray hopefully yesterday, will tell you a little bit about the number of vector instructions you're doing. You can also look at the assembler code if you want, and if, as you saw yesterday, if you start getting instructions like register names like ZMM, YMM, or XMM in the assembler, or instructions like VAdd, VMultiply, VSubtract, VLoad, VStore. These are vector instructions that the compiler is putting in there for you. Now, in general, we don't go down to the assembler code very often, but you know, for a little example, you can have a look and see what's going on there. And actually, I don't know if you remember yesterday, but some of the optimization, compiler optimization work I was demoing yesterday, when we looked at the different assembly sources, some of them were putting in, some of the compilers were putting in X instructions, so XMM registers and V sort of add, V multiply instructions. But that would suggest, actually, because they're putting in 128-bit registers, there may be a little bit of work we can do there to help the compiler vectorize up to the full width of the vector units. But it may not have given us any performance difference. But those are the kind of things you can look at. The other way you can check if your code vectorizes well, actually, I probably mention it later, but is by turning off vectorization, rerunning your code and seeing if there's a performance difference. Now, of course, if your code is memory bandwidth bound, it may be your code is vectorizing, but you're just not seeing any benefit from it because it's spending all its time loading data. But it's a quick and simple way of, you know, rerun my code with the vectorization turned off, and that's generally just a compiler flag, because the compiler's doing the vectorization for us. So we can say to the compiler, please don't vectorize this code, and see what performance difference you get. Okay, in terms of actually code requirements, the compiler generally needs loops to have a determinable trip count, so at runtime. That means that you can't have sort of unbounded while loops that are vectorized. So, you know, do loops or while loops where you break out of them, that's going to be a problem for vectorization. And that's because the compiler is turning your code into something which does multiple iterations of a loop at once. So it's going to do you know, instead of one iteration of a loop and then check what happens and then look at the conditions and stop, it's doing 4 iterations of a loop and check what happens and then stop. So it needs to be able to know that actually for this loop we have got 4 instructions, you know, 4 iterations left, so I can do that in vector form or not. You've got a question, Mark?
Yeah, I thought it best to speak this one rather than type it. The code I've got works on 3-dimensional space, X, Y, Z. Beforehand, he knows there's going to have 5,000 elements in Z. That's accumulation in time of something. And so each layer aggregates. So he does integrations. So his loop, his vectorizable loop, Z, the innermost loop, it changes each time step to being longer and longer until it achieves the 5,000. Should I actually change that to always do 5,000 and just have 0 information in the other areas?
It's a good question. Possibly. It may be that actually what you want to do there, and we'll come on to see this, is vectorize at a higher level, loop level. So by default, the compiler will look at the lowest loop level. But there are tricks you can do to force the compiler to actually vectorize at a higher level. And depending how complex the loops are, it may be that actually you can just move it up a level where your x or your y, which I assume are probably fixed per simulation, and vectorize on one of those instead.
Okay, thank you. I think that is not going to work. I think I've got to still stick with the innermost. Anyway, I'll think about this, but thanks for that suggestion.
Well, we can come back to it when we see you can sort of specify, you can move the loop nest vectorizing, which loop it chooses higher, and see if that works. But if it doesn't, then if your inner loop is going to change over time, it doesn't necessarily matter as long as the compiler can see the sides of that loop easily when you compile. So it doesn't need to, the loop size doesn't need to be fixed, but the compiler needs to know what variable is specifying that loop size, and it needs to be confident that that loop size variable will not change during the loop, because that's the key for the compiler. It makes it hard. If the compiler loop size can change, then it makes it very hard for the compiler to automatically vectorize it. The challenge, of course, is that if the loop starts off very small and then gets bigger, the vectorization performance is not really going to help you when it's small. It's only going to help you when it starts to get bigger. But depending on how many times you're repeating that in a loop, it may still be beneficial.
Okay, thank you.
No worries. I see Mark is asking, is talking about whether vectorization, turning off vectorization helps or hinders streams, which is that purely loading data in once benchmark, but we've used a couple of times already to benchmark the hardware. And he's saying that turning vectorization off does impact the streams benchmark a bit. So it's interesting. It could well be that it's disabling the number of floating point units you can use. Without vectorization, you can only use one of the floating point units, not both. But yeah, we should have a look at that, Mark, and see exactly what's going on there, because that would be interesting to know. Okay. Loops must not contain functions or subroutine calls. For the compiler to be able to easily vectorize your code. Now, again, this is not quite true because there are ways to do vectorizable function calls we'll come on to see, and things that can be inlined by the compiler, or things that are intrinsic functions, maths library functions, those kind of things are usually fine. But calling your own large routine inside the loop will restrict the compiler from being able to vectorize that, because it doesn't know what that routine is going to do, and there's all sorts of overheads with calling functions as well. Loops must not contain any branches or jumps. Now, again, this isn't quite true, but to get the best performance for vectorization, you don't want any flow control change inside that loop. So you definitely don't want any jumps out of a loop, because again, this is the same problem as the loops must have a determinable trip count or determinable size. But also branches make it hard for the vector functionality to be the same everywhere. Now, it is possible the compiler can do things like what we call masking instructions, which actually say run this vector instruction, but don't run it on all the data, because some of the data are in the if statement and some of the data in the else statement, and it can do fancy things around that. So it will still vectorize, but in general, that still impacts your performance. So if you can get away without doing branches inside your loop, and actually this is true for any loops, any performance, vectorization or not, if you can get away without the branches being inside the loop, you will generally benefit the performance you get from the processor, because there's often an overhead of instruction processing and an overhead in the processor itself on dealing with those if statements inside your loops. And if you don't need them in there, if it can be moved to a higher level, for instance, then that will give you some performance benefits. Even if we have branch predictors and things like that, but even there's some overheads in. There can be some overheads in branches that are not taken. And as I said already, the loop trip count, so this is how long your loop is, really depends on really depends on the size of the loop being good to give you good performance, and ideally multiples of a vector length, so multiples of 4 and multiples of 8. Now, you don't need this for vectorization, but you get best performance there because, as we'll come to see, you don't have to do the extra instructions at the end, which we need to do the vector, to do the correctness for vectorization. Just like when we saw unrolling the loop. When we unrolled a loop, we had to put in a special loop at the end to do all the remainder instructions. In vectorization, when the compiler is automatically vectorizing for you, it needs to create a special version of your loop, one that's vectorized, and then one at the end, which isn't, to do all the instructions which it couldn't vectorize. So this is exactly what Mark Bull has just put in the chat. So the compiler generates these special loops, what we call a remainder loop, and actually it also generates one called a peel loop, which are there to deal with the fact that the number of loop iterations might not divide evenly by the size of your vector registers, and if not, it needs to deal with that number of instructions, number of loop iterations which don't fit in the vector units properly with these different loops. But if we can avoid those, then we get better performance. But the key for the loops is this, these things: no branches or conditionals or jumps in there, no function calls, and a determinable trip count. So this doesn't mean it needs to be known at compile time. It can be known at runtime, but the compiler has to know that it won't change whilst the loop is running. Now, I think in Fortran it's illegal for you to change the loop counter whilst the loop is running, so I think that's fine. But in C, all bets are off because you can do pointers and you can do all sorts of nasty things. So you have to be a little bit careful there. Just like in OpenMP, loops must have no dependencies between iterations. Otherwise, the compiler will say, I'm not going to vectorize that because there's a dependency here. I can't do 4 iterations at once because the iterations depend on each other. But reductions generally are okay. So the compiler can do things like OpenMP reductions to deal with that, as long as there's not too many of them. And also, the compiler won't like if you have what we call induction variables. So this is where you're sort of adding up a number as you go around and using that to reference things inside the loop. Commonly used in a lot of scientific codes, but you can generally replace it with a loop counter or some variation of a loop counter, and that will get away from it. The problem with this here is that the value of index depends on the previous loop iteration, and that depends on the previous loop iteration, etc., etc. So it stops it being vectorizable. Whereas actually, if you could replace index by I, some function of I, index just becomes I times 3, then you don't have that dependency there anymore, and you can calculate what index is for each iteration of a loop, and you can get around that. There are some keywords we can use, such as restrict in C, and particularly this is for sort of C and C++ codes, which lets the compiler have more confidence about things like loop bounds and pointers being used inside the loop, so that it's not worried that data may be overlapping or change as the loop's going on. But quite often the compiler says, actually, I don't want to vectorize this loop because it looks like it's got dependencies in it, but it doesn't really have dependencies in it. You can check the code by hand and say, actually, no, I've had a look, and those things you think are dependencies really aren't. And then there are ways to tell the compiler this and let it override its caution and force it to do the vectorization. Now, of course, if you tell it that and you're wrong, then it's not necessarily going to produce the correct results for you. So, with great responsibility comes great power. You can override the compiler and make it do things, but just be aware that that can also generate code which is incorrect. And then for good performance, ideally we expect data to be aligned. And so we'll come on to talk about what this means, but basically it means that we want data to be in such a form in memory which we have a minimum number of loads and stores we need to do to get that data to and from cache. If we can do that, then we get our best vector performance. And likewise, unit stride through memory is best. So that means, you've got an array, you access element 0, then 1, then 2, then 3, then 4, then 5. Vectorizing that gives you better performance than, say, accessing unit element 0, then 2, then 4, then 6, then 8. Because in the second case, when you have to access, every other element, you've got to load twice as much data in to get the same number of vector operations. And loading and storing data is very expensive. So if you can have data access patterns which work unit stride data, then that will give us our best performance. How do we get our compiler to optimize, to produce vector instructions? In general, the compilers we have on Archer, the Cray and the AMD ones, generally define as -02 and above, it will try and vectorize your code. And that's generally the default on these compilers anyway, so you don't have to add that in. Again, generally, you need to tell it what hardware you're building for, so it knows the vector units and things, the instruction sets you're using. This would be on Archer, march equals zn ver 2. But again, as we said yesterday, you don't need to do this for Archer 2 because on the Crays, this is automatically added in for you. Other compilers, you need to do other things. So the GNU compiler, you may have to turn up to 03. You may also have to put in this command here, which I don't actually have, which is -f tree vectorize to make the GNU compiler vectorize. This changes with the versions of GNU compiler you're using. So I haven't checked the latest ones we have on Archer 2, but I'll have a look after we've done this lecture and we'll see. It may need you to add an extra flag in for GNU to force vectorization, but I don't think it does anymore. It certainly used to. I don't think it does anymore. You can turn off vectorization with -f no vectorize for the AMD compilers. This is the C compilers here, AMD or Cray C compilers. And you can also get information from the compilers on whether it vectorized your code well or not. So for the Cray C compiler, you've got this -rpass mist equals loop vectorize equals -rpass analyze equals loop vectorize, and that will, when you compile, generate a lot of information for you. For Cray Fortran, it's -hlist equals all, and for GNU, it's -f tree dump tree vec all equals in a file name, and that will give you these kind of things. For the AMD, yes, okay, so this is exactly the same thing being said here. And we can also look in the CrayPat hardware stuff for these counters if we wanted to. GNU actually offers you a bunch of different ways of saying how did I vectorize. So you can also get further information from GNU on the optimization the compiler's doing by using this -f opt-info all, or by using -f info vec mit. And so there's actually a range of different things we can use to get there from the compiler, and most of them will give you something useful. This one here, the dump tree vec all, is quite a good one, but opt-info all is also reasonably sensible. It just produces quite a lot of information when we do that. Right, okay, so yeah, as I've said, we don't want to have any dependencies between iterations. So something like the compiler being looking for things like this we may say there's a dependency here, and I won't vectorize this loop. And as I've said before, we can get around some of this by taking things which are really induction variables, where we're just counting something up and using it elsewhere in the loop here. Like I've got a count variable, I add 2 onto each time and look and use it for an index. I could just replace that by versions of an induction variable, so versions of a loop variable, I in this example here. Sometimes we may have to promote scalars to vectors, so a single dimensional array. So if for instance, we wanted to go through and create a set of totals like this, and the compiler, the specific compiler we're using says that's a dependency, and I can't vectorize. Some compilers will and some won't. We could turn total here into an array with an entry per loop index. Then each iteration uses a different element of total, and then once you've finished your loop, you can have a secondary loop at the end which goes through and adds that up. And of course, that's because all the data is already produced, and that probably is easier to vectorize. But even if it's not, that might be a sensible thing to do for your loop. You're using a bit more memory, you're using a bit more storage, but you're enabling you to vectorize a large loop by adding a little bit of work at the end. So it depends, again, it depends on how big this loop is you want to vectorize. But if this is the only entry that's stopping a large loop being vectorized, which is going to give you good performance, then turning it into an array and adding a small loop at the end to sum that up will still give you better performance if it lets you vectorize the whole loop than it does by leaving the loop non-vectorized. As we've also said, if you can move conditionals and branching operations outside the loop, sometimes you can have things which are maybe not quite as nice in terms of from a software perspective, but two versions of a loop, one for one part of the if statement and one part for the other part, and just replicate the loop entirely. And then that may let you move a loop, if statement from inside a loop to outside a loop to give you that vectorization potential. And as with all these things we're doing with optimization, there's a trade-off between changing your code to give you better performance and impacting some of the nice, software engineering code maintenance features that you may have put in your code. So there's always going to be some tension between those kind of things that are worth considering. And as I already mentioned, if it's a small loop and it's not got much work in it and the trip count is always quite low, then you may be able to vectorize it, but it may not be worth it because you don't get very much performance overhead of that. So if you're going through your code and lots of time's being spent in lots of small unvectorized loops, then there may be things you would want to do like combining loops together, loop fusion and these kind of things to give you one bigger loop that can be vectorized in its entirety, if that's kind of possible. So here's an example in C. This kind of code here, I've got a function. It's a nasty code. We don't often see code as bad as this for vectorization, but this code here is hard for the compiler to vectorize. So we've got a number of things going on here. We've got data coming in as pointers here, data 1, data 2, data 3, and index. We've also got the loop iterator in C as a pointer here. Okay, it's perfectly legal C. Then we've got this lookup J from index I, and then use J in storing my data here. Now, a number of these things the compiler will complain about. Firstly, it doesn't like data 1, data 2, data 3, and index being pointers. And that's because in C, there's nothing to stop actually data 1, 2, and 3 all pointing to the same array, or to the same array but slightly offset. And if that was the case, then actually if you took this loop and unrolled it or vectorized it, then you might get the wrong result because you're not doing the same thing. If data 2 and data 3 are one element below data 1, slightly offset from data 1, but the same array, then vectorizing it or unrolling it will give you the wrong answer here. So the compiler by default will just say, look, you've got data in here, I don't know what's going on, I'm not going to vectorize that. Likewise with this loop counter here, or this loop bound here, loop trip size here, it doesn't know that this can't change because it's a pointer. It doesn't know that this can't change as the loop is executing, because index or data 1 or data 2 or data 3, you could all alias this one here and change it. And because of that, it can't expand this loop into a vector loop because it doesn't know that any given iteration, I may suddenly change to be bigger than or less than loop size. In fact, loop size may suddenly change, so I is no longer less than it, and the loop has to terminate, and it doesn't know how to do that. And then likewise, there's this sort of J index dependency here, because index and data 1 and data 2 and data 3 could all be related. It doesn't know that this J here is not actually being calculated by this update here. So it thinks there may be some kind of dependency here. And so in C, it's pretty easy to fix all these kind of problems. We can use this restrict keyword here, which actually says, here I'm guaranteeing you, compiler, that none of these pointer references overlap at all. So that gets rid of that altogether. I can take this index, which is my loop pointer, and then just copy the data into a local variable, which the compiler now knows is not, it can see is not changing beside this loop. And so it's going to be happy with this kind of loop bound here. And I can tell the compiler directly, you may think this index equals J, and then J used down here as a dependency. But actually, I've looked at my code, I'm happy it's not a dependency. And so I can tell it, and I can tell it with these things like a compiler pragma here. So here we're using one called hash pragma ivdep, which should work on the GNU compiler and the Intel compiler if that's one you're using. There's also the same for the sort of AMD and Cray C compilers, which both use Clang now, with this hash pragma Clang loop vectorize enable here, or for the Cray or AMD Fortran compilers, where you can use in Fortran uses ivdep pragma over here. And so that, in general, the compiler will be much happier about vectorizing this here. The only thing that we haven't fixed there is data alignment, which we'll come on to have a look at next, because that's the other thing which the compiler will either say, I don't want to vectorize this because data is not aligned, or it will vectorize it, but it won't give you good performance. Here's an example of a loop that the compiler would be unhappy to vectorize in Fortran as well. So in Fortran, we generally don't have the same issues of pointers and these kind of things overlap in memory, although you can do pointers in Fortran, but people don't tend to. But here we've got example of a loop nest. Now remember, the compiler is going to try and vectorize this innermost loop here. This innermost loop has this X variable here, which is added up as we go around based on the values of I and J, and initialized at this point here. So immediately the compiler is going to say, well, there's a dependency here on X between loop iterations. So I'm not going to vectorize that. But you can actually say, okay, so I'm going to slightly restructure my code, turn X into an array, like we said before, and then have a different X for each iteration of this inner loop here. Each of those initialized by this first loop we've put in here, and we can move that dependency out now. So there's now no dependency between the loop iterations, because each one of X is only dependent on its current loop iteration because it's already been initialized, and that would let you vectorize that loop instead. Okay, I see a bit of chat has come, a bit of discussion on this has come back up on the chat around data alignment. So the challenge with vectorization, as we've already discussed, is that the compiler and the processor is really very simple once it comes to do vectorization. It loads data in to a vector register, and then it does the same instruction on that vector register, and then it stores data from that vector result out. And so all that functionality is really dependent on the data being aligned, sort of loaded and stored in these vector registers in the correct way, so that the first instruction works on the first, the first part of the vector instruction works on the first bit of a vector register, and the second part of the instruction works on the second bit of a vector register, and the third and the fourth and the fifth and the sixth and the seventh and the eighth in this example. Because if your data is actually offset here, and you just want to do your vector instructions on A, and you load data in from the cache line where A is, unaligned, but actually A0 will be here and A1 will be here, 2, 3, 4, 5 here, and this data at the beginning here would be something other than A. And if the instruction went away, it would work on data that you hadn't told it to do. And so you end up corrupting your data by doing work on data which isn't there. So the compiler and the hardware knows it needs to get this data in the form that it's aligned with the vector registers, so that you're working on the correct data. Now, the compiler and the hardware can deal with you not aligning your data, but as has already sort of briefly been discussed, what happens is it generates multiple different versions of your loop, one of which is fully vectorized, that's called a kernel loop. And it also creates this peel loop and a remainder loop. And the peel loop is to say, okay, your data is not aligned, so I'll do the first X many elements of your vectorization in serial, in non-vector instructions, until we get up to a point where your data is aligned on a cache line boundary or on a vector register boundary. And then from there, I'll start doing vector operations. So that's the peel loop. That's at the beginning. That's if your data is not aligned. At the end of your loop, just like when we saw loop and rolling yesterday, if your array is 50 elements long and your vector register size or your vector width is 4 elements, then the first 12 chunks of 4 will vectorize fine, but from 49 and 50 they don't fit into a vector register without some spurious data at the end, and so the compiler will also generate this remainder loop to deal with those 2 extra elements at the end of the array which don't fit inside the vector unit size nicely. And again, that will be run in serial rather in a vector using vector instructions, because the data is not there to run the whole vector width. So with unaligned data, we have these this work to do to create this initial peel loop, which will have to do some instructions, non-vector instructions to start with. There's also the remainder loop at the end, which if we don't evenly divide, we'll also have to do a little bit of work. But if you align the data, actually we can get this minimum data loads, cache line loads, and instructions for the vectorization. So we'll need the minimum number of loads of data from memory, because we're just loading up full chunks of cache lines because your data is aligned on them. We've got the minimum number of vector loads and stores because we're just loading up full vectors. And we don't have to deal with this peel loop at the beginning and all the overheads associated with that. So what does that mean? That means that we need to align our data and then tell the compiler the data is aligned so it understands that. And we do that using, unfortunately, a number of different ways we can do that, depending on what programming language you're using and what kind of data structures you're using, whether you're using dynamically defined data or statically defined data. So in the C and C++ environment, we would use these mmmalloc, mmfree functions, which create your data. So this is dynamic data. This is dynamically defined data in your application. mmmalloc and mmfree create aligned data. So you can tell it a number here. I put 64 at the end here. We could use 32, but 64 is quite commonly used to say align on 64-byte boundaries. And then this will create you an array which is aligned to these cache lines which we want to get our best performance. If we were doing this in Fortran and we were doing dynamic data, then what we would do is we would use this attribute here in Fortran. So we've got this allocatable data, and then we do this, when we define this array A, we also say attributes align and do it in that way. So that's for dynamic data for both C and Fortran. The thing to be careful of in C is that if you do mmmalloc, which is fine, you always have to use mmfree to free up those arrays. Otherwise, it will crash your program. If you have static data, so data which is defined at compile time, the size of array is defined at compile time, in C we can use this double underscore attribute double underscore. And in Fortran, we can use the same thing as we use for dynamic data. So we can use this attributes aligned. And there are some more details for common blocks in Fortran and derived types. You have to be a little bit more careful in Fortran to manually pad things out to get correct alignment, because derived types tend to pack in data structures well, efficiently, but in such a way as it ignores these align attributes. Multi-dimensional arrays we also have to care about. So you would have to align each dimension of your array if you're malloc each dimension separately, or you can do a single dimension allocate or malloc. But you have to be careful then of the sizes of your arrays, because in this scenario here, we've got a single dimensional array which we've malloc aligned, so the whole array is aligned. But actually, when you get down to the J loop here, these starting point for this J loop is not guaranteed to be aligned, because it will end up aligning on 15 element boundaries, which won't necessarily be aligned. So if we vectorize this loop, we could end up with problems here. Now, so that's how we align data, which is something we need to do for good vectorization. Once we've aligned the data, we unfortunately also have to tell the compiler we've aligned the data, because particularly these methods up here, malloc, free, the compiler doesn't actually know what they're doing. They're just function calls and to give it back pointers. So it doesn't know what you've done there. So once you've aligned your data, you also have to tell the compiler you've aligned it by doing potentially by doing any one of these different things here. So the most portable one these days is to use part of the OpenMP library and use this OMP hash pragma OMP SIMD aligned. And so you can put this on a loop, and you can say, on this loop, my array A is aligned at 64 byte boundaries. Likewise, you can do exactly the same in Fortran. You can also use this hash pragma vector aligned or bangdir $vector aligned in C or Fortran, and you put that at the beginning of a loop, and that tells the compiler for everything in this loop has been aligned. Okay, so this one down here, we're specifying individual arrays and telling it it's aligned. Up here, we can also say this whole loop has all the data entries that are aligned. You can also do things like specify the alignment for specific arrays for the whole program. So you can do it at a program-wide basis to say, actually, for the whole of this program, assume this array is aligned, either by using this double underscore assume aligned or in C, or this dir assume aligned in Fortran. And so both of those, any one of these approaches is possible. You just need to do one of them to get your sensible vector performance. There is also some complexity. I'm not going to dwell on this here because I'm running over time again, but there are a little bit of complexities in how we pass data in Fortran to subroutines. So if you're passing explicit arrays into the Fortran, then you can assume contiguous data. You may need to tell it it's aligned. But once we start going into assumed size arrays and assumed shapes arrays, we just have to be a little bit more careful. Now, I'm not going to go into details here, but if you want some more detailed clarification on this, it's in the slides, and I'm happy to take some questions afterwards on if this affects anybody. But Fortran can be a little bit tricky because it can automatically do you copies of data into and out of routines. And if it's doing that, then it may automatically align that for you. But if it's not, if you're telling it the size of arrays, it might not automatically align that for you. So there's a little bit of complexity there. So here's an old example using old Cray compilers of the kind of approach we're looking at. This is the code we saw before where it said it's not vectorizing, excuse me, because it was unhappy that there was this recurrence of this x variable when we're going around this routine. And then when it was changed, we took the code outside, initialized it, and it let the code vectorize, and it went faster, you know, not 100 times faster, but about 40% faster for this is actually on Archer rather than Archer 2. But this is just in here to see the kind of output you can get from the compiler. So for the Cray compiler, it'll tell you things like the loop was not vectorized, the loop was unrolled, and you can go and have a look at it. And here it's saying, okay, we've interchanged these loops 43 and 44, so it's actually doing some changing of the loops. It's fused some loops together to make a bigger vectorization space, and then it's vectorized and unrolled the loop 4 times to give you a better performance. Okay, so the final thing I wanted to say was we've already seen a little bit, but some of the OpenMP functionality from OpenMP 4 is directly designed to help with vectorization. And this can be useful because actually a lot of the stuff we've talked about in here, these hash pragma, these compiler directives, can often vary between compilers. The nice thing about the OpenMP stuff is that it's compatible across compilers. So you can use that to specify your vectorization and your alignment, not to create your aligned data, but to tell the compiler it's aligned. And that can be useful because it lets you run across multiple compilers, across multiple computers. To get it to enable the functionality, you have to turn on OpenMP compilation for your code. But apart from that, it should just work as normal. The main directive is this hash pragma OMP SIMD or bang dollar OMP SIMD. And that you put before a loop, and that tells the compiler to vectorize that loop. And it's important here, this is not a hint, this is you telling the programmer, you as a programmer telling the compiler, this loop can be vectorized. This loop is safe to vectorize. So if you get that wrong, of course, you can break the code. And then there are various things you can tell. So this is one of the ones you can use to force the compiler to vectorize a different loop in your loop nest. So you can vectorize not just the innermost loop with this, you can sort of compile it to vectorize at a higher level. You can tell it sort of things like the size of vector units you're using, various things about different variables in there. And you can compile it with a for loop or a do loop to vectorize and parallelize that. And actually, we don't go to this in huge amounts of detail, but there are further functions from OpenMP which let you decline further pragmas from OpenMP which let you declare things like small functions as vectorizable SIMD functions, which can be included inside loops. And so again, if you want more information on that, we have further material. We just don't have the time to cover it all in the lectures on this course. So do let me know. So that was a quick tour of vectorization, and I know there's been some questions already, but has anybody got any more questions on or comments or things that didn't make any sense on vectorization? I appreciate it's getting towards the end of the day, and so there's a lot of information coming at you quite quickly. Hopefully the practicals help cement this, where there's a couple of things where we can play with vector things to improve the performance. Look at little examples where the code doesn't vectorize, the compiler doesn't vectorize. We can look at the compiler reports and then say, try and get it to vectorize them. Not particularly looking to see the performance of these loops, but just looking to see what that process looks like, what compiler vectorization reports look like, and then what you can do, what you need to do to the code to fix that. If there aren't any other questions, then in the last 15 minutes before the break, I'll give a very quick overview for some of the memory optimization stuff we care about as well, because memory is also very important for performance. And as has already been said yesterday, and you're probably already aware of, one of the dominant issues in high application performance these days is that memory is much slower than processing. So fetching data in from memory is expensive in terms of processing time. So that means that what we want to do is optimize our use of data that's already been loaded, reuse data where possible, and that means structuring our programs for temporal and spatial locality, so reusing that data in the cache nicely. And it also means accessing data in memory, from memory, in sensible orders if we can, will give us better performance. Now, in general, the compiler just does what you tell it to do with memory. So it doesn't really understand memory particularly from a hardware level. So you tell it, I've got an array, it's got 1,000 elements in it, then it will use that array in the way that you've told it. Now, the compilers actually these days can be quite good at looking at memory accesses and saying, look, this doesn't look like it's contiguous and that's not going to give you good performance. But they're still generally bound by the things you've told them as a programmer, your memory structures you've given them as a programmer. The memory structures we use primarily in high performance computing for most applications are, arrays. So integer indexed arrays of dense data, something like this in C and Fortran. This is a 3-dimensional array, A in C or Fortran. In reality, you could also solve that as a 1-dimensional array of 100 times 100 times 100. Now, this one on the left-hand side is a single FLAC data structure. The one on the right-hand side, the one on the right-hand side is a single FLAC data structure. The one on the left-hand side is stored as a set of arrays combined together to give you that full data set. There is some slight overhead in using this format where we go through this array addressing notation rather than using a flat array and notation like that. But in reality, you should be able to see these two things as equivalent in terms of performance. The big thing that you need to care about is sort of data locality and data access patterns. So what you want is your loop, and this is particularly important for multi-dimensional arrays. So arrays like these here where we've got nested dimensions of arrays, or single dimensional arrays like this where we're accessing it as if it was a multi-dimensional array. And what we're looking to do here is make sure that our access order match the pattern which is optimal for cache reuse. So compilers will try and fix these problems by transforming loops if it notices you're doing things wrong here. But there's only so far a compiler can do. So what we want to do is give the compiler and give your code good spatial locality. Now, of course, I'm sure many of you are aware of this, the nasty thing is that the way you do this varies between C and Fortran, C++ and Fortran. In Fortran, the loop index or your array index on the left-hand side, the leftmost index, is what's called stored contiguously in memory. So stored in a single chunk in memory. So all of the I loop from 1 to n here is stored in a contiguous chunk in memory. And then in Fortran, all of the j loop, every time you go around the j loop, you move on to a different chunk of I, and each one of those chunks is in contiguous. But when you're moving through the j loop, you're stepping through, n elements in memory. So that means that this loop here is going to access our memory inefficiently because j is the innermost loop, j is the fastest index. So I want to load up ji. That'll load the whole chunk of I up and get one element out of it. And then when I move on to the next iteration of j, it loads up a whole new chunk of I to get one element out of it. And likewise, it just keeps moving on like that. So in this scenario, what we want to do is reorder these loops. So actually the I loop is the innermost. Then when first iteration around the I loop, we load up a chunk of I into cache. And then after that, we just keep referencing that chunk of I until we've finished, and then we have to load up another chunk. And that means that we have one load from memory into cache for a large number of operations, compared to this left-hand side where we have one load from memory into cache for every iteration around this loop. And so we get our best spatial locality here. In C, it's the opposite way around. In C, the rightmost loop index is the one that's stored contiguous in memory. So this here for A, all of the J's are stored in a chunk for every I. And so again, this loop is wrong because I'm going to go around this loop. I'm going to get a whole chunk of J for this I, then move on to the next iteration, get another whole chunk of J in for this I. And that will be expensive compared to just reordering the loops. And now over here, I'm going to load up, when I first do my first I, I'm going to load up a whole chunk of J and then just use that J until I've exhausted it in the cache and have to load up another chunk. Now, of course, all of these codes are correct in the sense that they will all give correct results. But these codes on the right-hand side will give you better performance than these codes on the left-hand side. And then the other thing to bear in mind here, of course, is that compilers nowadays can spot some of these issues. And particularly loops that are very simple like this, the compiler will potentially, some compilers will look and say, actually, you're doing something stupid here, I'll reverse these loops for you here. And we saw that in the previous lecture where the Cray compiler said, oh, I've interchanged these loops for better performance. But in reality, of course, your codes are not as simple as this, and they're more complex loops, and it becomes much harder for the compiler to spot poor access patterns inside complex loops. So this is the real, if you get this wrong, you get very slow performance. If you get this right, you get much better performance. Dynamic sized arrays, we don't, let's not worry too much about dynamic sized arrays actually. Dynamic sized arrays do require a little bit more instructions to work, but we don't need to worry too much about this in terms of performance. As I say, there are some other things you can do to optimize your code in more detail once you're down to that kind of level, but we're not really going to be too worried about that. We can see challenges when we start putting structures and arrays together. So there's often a tension when developing your application about how you store your data to give you good performance. And so we do see these examples of people using arrays of structures or structures of arrays. And some of those can have quite a high impact on performance when you're in terms of reuse of data loading and data storing. So here's an example in C. On my left-hand side is an array of structures. So I've created a particle object or a particle structure. It's got an X and a Y and a Z position, an index and a mass. And then I've got an array of particles. Okay, and so this is an array of structures. Nothing wrong with that. Or I can create a structure where inside that structure I have X, Y, and Z index and mass arrays. Each one of these is a full array. And then I can use that structure. So that's what's called a structure of arrays to store my data in them. Now you can imagine which one of these gives us good performance for a particular application really depends on how you use the data that you're storing in these structures or these arrays. If what you do is you load up a particle and then you do a lot of work on X, Y, Z, index and mass sort of all at once, then an array of structures can give us good performance because we load up the data, we reuse that data, we use that data, and then we move on. If, on the other hand, you want to know all the X coordinates or all the masses of particles, and you iterate through all your particles and just look at the mass, then you can imagine that this array of structures is less efficient, because you're going to load up 5 elements here with 4 doubles and an integer, but you're only using 1 double. So you sort of you're loading 4 times 1/5 of the data is being used, 4/5 of the data is being loaded, but for no reason. Whereas over here, if you can just load up the mass array, then you load it up, you go through that all, and you get your data that you need, and you're reusing all that data here. So there's always going to be a tension between designing your software nicely with having some of these nice structures which are understandable and easily maintainable, and getting best performance depending on how you're using them here. And you can easily imagine that actually, if for a particle, you probably want to use the X, Y, and Z things together, and the mass and the index together. Well, who knows what the index is there for, it's just made up. But you can imagine you don't do very many operations where you just look at the X points of all the particles, but you probably want X, Y, and Z. But you may do lots of operations where you just look at the mass and you don't care where they are. And you may want to then separate those things out into structures of arrays, or these kind of things. So you can do that. So the array of structures is good for temporal locality, as long as you're reusing the data inside that struct lots. The structure of arrays is good if you're reusing one part of the structure, because we have these we can access arrays contiguously and vectorize them, but it's not quite as nice as a design pattern as this one over here. We've got a particle structure, and then you can do arrays of structures arrays, or these kind of things. So you can do a small number of particles together, and then lots of those small numbers of particles together to give you a bit more vectorization potential. So you can imagine if you were, adding all the particles positions together, you'd want to be able to vectorize like this, so all the x's could be added to all the other x's and all the y's and the z's. Okay. So objects are generally fine. Early days of object-oriented programming, there was quite a high overhead to using objects, and that has come down a lot over the years. The only thing we would say generally with objects is that if you have very low level, get and set methods, functions for accessing individual data elements for your array, and that's used inside your kernel, then it's likely to be impacting your performance, and you may need to abstract your object a little bit to a higher level, and maybe have a function which says, give me this array, and then you can work on the array, rather than saying, give me element 10 of this array, give me element 12 of this array. So those are kind of things to think about. Trees and lists, quite very commonly used in programming languages like C. C is very good for flexibility in programming, but really hard to sort of vectorize and optimize the loops of those kind of things, because the access pattern is hard to predict, and the contiguous nature of the data is hard to have a look at. So yeah. The other thing that you can see happen is you can, for applications, see conflicts over cache line usage sometimes occur. So it can be that, it's less of a problem these days because modern processors have these things called 8-way or 16-way processor caches, associative caches, which means that they can have multiple different data structures map into the same point in the cache. More than we used to be able to do in the past. But basically the way the virtual memory and the caching hierarchy works is that arrays, chunks of arrays, map to a certain cache line. And it is possible that you can have scenarios where chunks of different arrays, array A, array B, array C, all end up matching to map into the same cache line, and you get this sort of cache conflict, just like you see in OpenMP with competing for data, so sort of cache thrashing that way. You can do the same between arrays. And so very occasionally you can get to a point where you get issues with sort of cache alignment like that, where everything looks like it should be working fine, but you have a high cache miss ratio and high cache eviction ratio. And in those scenarios, it is possible to pad the arrays to get around this. But it's less, this is something we used to see 10, 15 years ago. I think it's less common these days, unless Mark has seen it more frequently than I have, but it tends not to be an issue nowadays. And then, we had questions yesterday. What does good cache usage look like? Bad cache usage look like in terms of hardware counter reports? So here's an example here. We've got data cache hit ratio and miss ratio here for us of our L1 cache and our L2 cache here. And what we can see here is that our L1 cache hit ratio is only 89%, which just sounds like it's high, but in reality, that's going to give us performance problems, because it's saying that every 9 instructions we have to go and get some data for L2 cache, and there's going to be something like 4, 8, 16. I can't remember what on this instruction cycle cost to doing that. So you want to avoid that. Whereas we can alter our code and get good cache alignment, and we can go up to something like 95% or higher. Then we can see our ops per miss going up and our performance improving from those kind of things. And there are ways we can do this. So actually, this is quite a big topic, and I want to give you guys a break. Attendees a break now, but there are ways we can do this. So cache blocking is one of these ways we can do this, where we actually want to store chunks of data in the cache and then reuse that as possible. And so cache blocking or loop tiling or cache tiling takes an approach where we take our multi-dimensional array like this, and then instead of going through it contiguously in one dimension and moving on like that, we go through it in little chunks and reuse the data like that. So we can break our 2 loops into 3 or 4 loops, and then move over those in little chunks. Now, in this example, it doesn't make any sense to do this, right? It's not going to give us any performance benefit here doing this. But where you've got data being reused between different arrays, or different arrays with different access patterns, then it can give you a sensible performance improvement. Then also you can see this approach being used to try and help with vectorization as well. So there are times when vectorization won't work well because there's these loop dependencies between the lines, but it cares about the element j-1, but it doesn't know the element j-1 if you vectorize this loop. So it'll say, I'm not going to vectorize that because you've got a dependency here. But actually you can do a little bit of cache blocking or loop tiling here, so that our we've changed the layout of the data, right? We're going through it in a different order, but we structure it in such a way that the data that it needs to do the vectorization is there. So there's more structure in the slides if you're interested, but it's probably beyond what you need to do for this course to start with. So have a look at it. If you're interested in any of the details there, then do come back and give me a shout or drop me an email. Or send us a message, and we can talk about it in more detail. Does anybody have any questions? Thanks, Mark. So Mark's following up on the this sort of padding, whether you have to pad arrays to get good performance in case there's sort of this cache interference, cache thrashing thing that goes on. And yeah, as he says, you need about 9 arrays, different separate arrays, to be accessed inside a loop before you could get to a point where you're starting to override a an 8-way set associative cache. So it's unlikely, it's not impossible, but it's unlikely you'll see these kind of problems these days. Any questions? Okay, if not, then we will take a break here. And then what we come back to after the break is just practicals. So you can just work through the practical sheet, either doing the existing, so the MD optimization stuff, still looking at the OpenMP molecular dynamics thing that you were doing with Mark this morning, or move on to the vectorization examples and some of the other things in the handout sheet. We'll take a break here, come back at 3:30, and just keep going through to the end of the day. But thanks. I'll have a look at that, Mark. The only thing I would I think say now is just a quick reminder. Yeah, you're more than welcome to come back and ask questions and do the practicals with us here, or do the practicals in your own time. And I'm quite happy to take questions over email or these kind of things if anything comes up. I'll stick my email here in the chat if you need it. If you're going to take a break here and not come back, it's a good time to remind you have that feedback form for the training, which is useful to us, both in sort of letting us know. Let me see if I can get it up. Letting us know what you thought went well or not well, and what you would change, what you wouldn't change, what more things you would have liked to have in there or less, and just in general what you were feeling. So there is this. It's actually through the Cray site, I think, the survey for this one. But let me see if I can share it. Yeah, it's here. So if you just go onto the Archer 2 website, training courses, this course we're on today here, and there's a feedback form at the bottom here, and you click on that. There's plenty of stuff you can put in here. In reality, the most important things we want in here is this top one. How overall, how would you rate this training event? All the rest is optional. And yes, any feedback you have is welcomed and will be useful. So hopefully we'll see you back here at 3:30 to go on with the practicals, and any questions you have, let us know. And I'll have a look at that slide, Mark.
Hi everyone. Please let us know if there's anything we can help you with, either directly with the exercises or with any of the course material. If you've got any questions come up, or you want to ask us about your own application codes, then please take advantage of that in this final session.
Okay, there was a couple of people asking for an example of MapMol with blocking implemented in it to see what that looked like. I've gone Fortran here. I can get a C example as well if that'd be useful, but I know Mark was interested in the Fortran to start with. So this is the original code, a bit dim on your display. Let me have a look. Let me see if I can change the. Is that better? Good. If it's not, let me know. I can put it into black and white probably. Okay, so this is a more sensible example than we have in the lectures, but sort of highlights more why you may be interested in blocking a piece of code like this, because we have these sort of different access patterns for the A and B arrays compared to the C array. So we go through this here, and in fact, of course, we're doing this in the wrong order here for the C array, because ideally we would be going through I contiguously for the C array, but we have these different setups for that, and we could rearrange. There's nothing to stop us rearranging these loop nests to change the contiguousness of the accesses. But what blocking lets you do is, iterate through the B and A arrays for a given K, whilst keeping some of the data in cache, rather than going all the way through all the J's, and then coming back around and you move on in the I and you've got to go through all the J's again for B for a given K. We're going to want to go through in small blocks to try and keep it in the cache. And so an example of doing that in the way we have on the slides. And there are multiple different ways of doing this. We could block all three loops, the K loop, the I loop, and the J loop. We could block the J loop only, or the IJ loop. And well, it doesn't really make much sense to block the J loop only, but we could block the IJ loop or IJK loop. I've just blocked the I and the J loops here. And all we've done here is added 2 extra loops, extending the loop nest, where the first extra loop takes this one here, the I loop, and says, okay, now we're going to go for in block size, chunks of block size. So I've set out 1 at the moment, but normally that would be something more like 4 or 8 or 16. And then that will say I of 1, start off at 1 and then go to 17 and then etc, etc. And then down here we have this I loop, which does all the iterations in between. So it starts off at 1 and then goes up to either 16 or the end of a loop, this n here, whichever comes soonest. And we do exactly the same for the J loop here. And then down here we can just replace our IJs with IIs and JJs. And then that should go through the loop and do this in smaller chunks. Oh, I didn't need to be in the right mode there. And we can see actually that if we run that now with, so I'm again benchmarking here on the login node, so it's not perfect, but if you run this without loop blocking, it runs in about 12 seconds, 12, 13, 14 seconds. Here, this is run with a loop block of 1, and actually you can see it's gone a fair bit slower. We've added extra functionality in there that isn't needed. The loops are very small internally, so it's not going to do any of the optimizations we'd like to do, so that really slows it down. But if we can change that, we've got a 16 block size, so let's see what that looks like in terms of loop blocking. Now, this is always a slightly dangerous moment live demonstrating, because I'll have made a mistake and the thing will come out much slower. Okay, so no, it doesn't. Here we go. So here we've got the same result as we've had here before. So the results haven't changed, but here it's running around 9 seconds. Here with a loop block size of 1, it ran in 31 seconds. If I take that down to a block size of 8, it should affect the performance slightly as well. It maybe get down below sub 9 seconds, I think. Again, it depends. Oh no, it's gone up there, so it's now up at 11 seconds. It depends a little bit of what else is going on the login node at the time, right? So it's not a perfect, experiment, this. And we'll go the other way as well. That 16 was the fastest we've had so far, the block size of 16. That's 8 of 11 seconds. And this is going to be, as you say, variable for, this is a block size of 4, so it's 12 seconds. Variable for cache size and array size. you know, what kind of blocks are useful here. Cache size, translation, look aside, buffer size, these kind of things will make a difference for that. Let's see what 32 does. Yeah, so 32 is slightly faster, but probably within the noise. So that's an example of how you would do the kind of basic blocking. As I say, we could block the K loop as well, and that may have a different impact, and do 3-dimensional blocking, but that's sort of an example. Is there any questions on that?
Hi, Adrian, Mark here.
Hi, Mark.
So I haven't looked at the list file, but what does the vectorization, if you actually turned on vectorization, how would that deal with this?
Well, that's a good question. So the vectorization is going to have some impact here because it potentially is, you're going to have smaller loops on the inside. So we want to make sure that inner block size is probably big enough to do some kind of vectorization. So again, you're restricting yourself to vector that JJ loop there. What we could do though for an optimization here is do some collapsing of these inner loops for vectorization. So we could collapse down the II and J loop into a single loop at the compiler level.
Oh yes, that's fusing.
Yes, yes. So we can do that ourselves, but the compiler can also we can also sort of suggest to the compiler that it collapses these kind of loops into a single address space for the vectorization as well. So that is also possible. So if I did OpenMP SIMD vectorization directive just above the II loop, we might be able to vectorize both of those loops in a sort of linear space.
Okay.
But it's a good question. There is going to be a trade-off between block size and the vectorization of that inner loop. But something like a block size of 32, 64 should be fine. You know, and in general, your loop is going to be more complicated than I've got here. So it's not going to be a single C equals C kind of thing. It's going to have more entries in it. And each one of those will be a vector instruction, which gives you more scope for things going on.
So that's a tile of 1024 elements. And if the elements were doubles or singles might be important.
Yes, so that will have a difference. Yeah.
Yeah, and then you've just got to think there's 3 arrays. You got to think how much is each word, and then how much is each tile, and then which level of cache are you actually trying to block for.
I don't think the L3 came into it until you had much larger arrays. Is that right?
Yeah, L3. It won't be L3, but you have to. It could be either. You could choose to target either L1 or L2 here. I think probably, generally speaking, you probably care more about L2 than L1 for blocking.
And there's a phrase someone mentioned to me many years ago called cache victims. Is that something, a feature?
Yeah, so that's a design. That's a cache design thing. So that's rather gone out of fashion with now that caches are so widely set associative. So what some cache designs have is what's called a victim buffer. So when a cache block gets evicted from the cache, it doesn't actually go straight away to main memory. It goes into the victim buffer first, and then if it's the next thing to be accessed, it can get pulled back in.
Okay, yeah. I was wondering where that thing is. Isn't that what L2's role is?
No, this is just like a single block's worth of buffer on, and it could be on any of the level of cache. So if something got evicted from L1, it would just go into this little, instead of getting pushed down into L2, it would just get pushed immediately into this little buffer. And if the next block that gets accessed happened to be that one, it can be just pulled back in again immediately without it ever reaching L2.
Okay, cool. All right, thank you.
But say with it was kind of a little workaround for when you had like so direct map caches or two-way set associative, where you could have this problem of if you had two arrays that map to the same set, then you could get these constant evictions, and that was a kind of a sort of a dirty fix for those pathological cases. But now you've got like 8-way and 16-way set associative caches. It doesn't really make so much. It's not really so necessary these days.
And just harping back to the 80s, do you remember the red-black algorithm for something? That one rings a bell as well.
Yeah, Gauss-Seidel. Yeah, red-black
Yeah.
Gauss-Seidel. Yeah.
And whether that would sort of trash this sort of method. Yeah.
Well, you go. It's not great because you're basically doing strides of 2.
Yeah.
So your cache utilization, your spatial locality isn't so great. You're basically accessing every alternate element of arrays for that algorithm.
Well, thank you both, because this is really helping me with this serial code that I've got, because the coder wrote it, I think he was a C programmer, because all the indices are reverse, as in like he's got X, Y, Z, but Z is his innermost loop. So I'm having to reverse it all.
Joy.
Well,
Yeah,
it's a nice problem to have, that one, though, because it's one where you really can make a difference in performance.
Yeah. I've also got to work out what his checkpointing restart needs to be, because he hasn't got one, and it sits for weeks on his desktop, and if he crashes, he loses.
Oh dear.
It's fun, but it's an under the counter one, that one. Anyway, thank you very much. I'm going to leave you now, but it's been really, really helpful for me. Thank you very much.
Oh, you're very welcome. It's nice to know that it's of practical use to you.
It's definitely going to be used in the next few days. Thank you very much again.
Excellent. Bye. Cheers. Bye.